Hi everyone, this is Romin Irani. I work as a developer advocate at Google Cloud, and today we are going to be looking at software supply chain security. And my goal in this session today would be to make sure that you go back with a few messages around what are the things that you as developers would need to do in order to ensure that the software that you both build as well as consume is sort of protected from various risks that are there right now from a point of both attackers trying to put malicious code into it and even other vulnerabilities that you might just unknowingly use depending upon various dependencies that you use and so on. So let's get started with this. And first up, right, I just wanted to highlight a typical build process that's out there. And what you're seeing is just a very high level overview in terms of that. As a developer, you've got some source code and you use some dependencies. These dependencies could be like the other libraries that you use or your application depends on to build out. For example, if you're a Java developer, these could be jar files. If you are a Python, could be the pip libraries. If your Node.js could be npm and so on, right? So it's not that you're just a producer of software, but you're also a consumer of software, right? You are when you build your software is dependent on various dependencies or libraries that we are talking about. So you basically take your source code, you might use some other libraries, and there's a build process out there to produce the artifacts, right? And so you basically package it and then finally go ahead and deploy, run this. Now, most organizations that we have, sort of looked at over, and even as of now, right, will mostly focus on the last part which you see, which is deploy and run. They try to protect that environment, saying, hey, our production environment needs to be really secure. We don't want anything going wrong with it. That to us is core security. We think that's important, but we found that really speaking, right, it's the entire supply chain that you need to be worried about or you need to be thinking about because at each of these points, and I'll show that to you in a while, there are various attack vectors that attackers could use to sort of create trouble as you build out your software. So, just as a point to reiterate once again, right? Dependencies, of course, but the point again to make is that you're not just a creator or the producer of software, but you're also a consumer, right? And these dependencies or these third party libraries are the ones that you're also consuming in order to create your final product. Now, coming back to industry overview of what's going on right now, plus the entire supply chain attack vectors that I was talking about. Now, these numbers are a clear indication that malware of all kinds is increasing, number of threat actors are increasing, number of cyber attacks are on the increase, etc. So it's very important that you look at the entire landscape as well as pay attention to this whole thing. Now, coming to the different supply chain attack vectors that we were talking about, right? Now, this is the same diagram that you've seen before where we had the source, build, deploy, and run. But what you're seeing out here, which those arrows point out into, are various ways in which your software could be affected. So there are scope at so many points, as you can see. Someone could inject bad code. Someone could sort of compromise the build process that's out there. They could even, change the packages in some way or the other. Even in the runtime environment, someone could be trying to deploy a compromised image, so on and so forth, right? So the point over here is that if you look at the entire supply chain, there are various ways or various attack vectors that you're seeing out here, and it's quite vulnerable throughout, and not just in the final run or the deployment or production environment that we are talking about. So, as developers, right, and this is the message that I want to give in this particular talk, that there are three actions I want you to pay attention to. One is to manage your secrets well. secrets could be, think of it at a very high level, like API keys when you're using third party software, or APIs that are out there. They might give you an API key which you need to initialize at the start of your code and then make the calls to their software, right? That's how we do that. But really speaking, how do you store these secrets? How do you store these API keys? Where do you store them? Do you store them in the code? Do you store them in a container image? If you just check in your GitHub, or any other well-established secret stores that are out there to do that? So we'll talk about what's the right way to do that. Second, I've talked about this a little bit, is that dependencies are important, right? You're not just a producer, as I mentioned, but also a consumer of dependency. You use third-party libraries. Seldom is there any software today that's not written where you're sort of integrating or using other libraries to build your application on top of, right? So by dependencies or managing them over out here, we'll talk about a little bit more, but at a high level, you must be aware about what dependencies you're using. You must be aware about also the transitive dependencies that could be there, right? And whether these uh, uh, packages or dependencies that you are using, are there any known vulnerabilities that have been found out towards that? And third, which is also the a key thing, and if not the most important, is that across your entire development process, I showed you there are so many attack vectors, right? From coding, building, deploying, right? And so, how do you build out trust so that at each step, right, you will reject things that do not follow your development process? So, what I'll do next is I'll be going into each one of these actions. I'll be talking about a high profile attack that has happened in that area, and then what could be some of the best practices to avoid that. So, first up is managing your secrets well. And over here, I'd like to take in, this particular attack for a product called code coverage. Code coverage allows you to package your, snippets of code as containers and then run them into a particular customer's environment. Now, if you look at the sequence of steps that are given out here from 1 to 6, right? But just to make it simple for everyone, um, the attacker in step 1 found out that in one of the container images of this product, there was a key already present, right? Or the secret that was already present. The attacker got hold of that, secret, as a result of which he was able to, download that particular code, modify the code in order to do some malicious stuff, and then, put it back again. As a result of which, now step 3 onwards, right? This malicious code is available for the customers to now download and unwittingly or unknowingly use it, in their environments. And that's precisely what happens in step 4. They start using this compromised software. The software then has been written to sort of, I would say, read their environment variables or send sensitive information back to the attacker. And then obviously the attacker will use that additional secrets or passwords that it has got access to, and then attack the customer's environments more and more. So it all started, if you notice, by someone leaving a secret or an API key somewhere in the container image. So the question then comes up, where do we store these things, right? So let's talk about some of the best practices out here. So from a manage your secrets perspective, right? Stop storing your secrets in source code. We've all done that when we try out things from a demo perspective, right? But it shouldn't stay there. Absolutely no way you can put them in environment variables. Absolutely no way you can put them in your GitHub or source repositories, and so forth. So where do you put it, right? So the suggestion is use dedicated secret stores, as step 2 mentions out there. So most of the environments today give you dedicated secret stores. You store them securely, and at runtime you kind of access those secrets and use them in your code. So for example, Google Cloud has a secret manager. There's also HashiCorp Vault. So there are many such secret stores which are recommended as a way to do it. Obviously, even if you use dedicated secret stores, a further best practice on that would be that avoid long-lived secrets. Obviously, you need to keep rotating them frequently, keep them short-lived, and so on. And of course, nothing compares to following good hygiene and consistently using multi-factor authentication. So that's manage your secrets. Let's go on to the second point, which is manage your dependencies, right? And I'll cover a couple of examples or a couple of well-known exploits that have happened when it comes to dependencies. And first one is a very interesting one. There's a package called Browserify, which is quite popular. It's an npm package, Node.js developers, and it's quite popular in the community. Now, what one of the attackers did is used a technique called typo squatting. And what typo squatting means is that the attacker simply took this package Browserify, modified the code with some malicious actions inside of that, and then checked in the code into the community repository or the artifact wherever you have all the list of these packages available, checked it in with a slight difference in name, which is what you can see over here, called web browserify. As a result of which, when developers quickly want to get access to Browserify, download it for them, they go to that search and they type the word Browserify, and as a result of which, both Browserify and Web Browserify come up as results, and they, in their hurry, just download Web Browserify, which is literally the same code, but with additional actions which are favorable to the attacker. So what happens in step two is that the developer mistakenly chooses the wrong package. This package is obviously then installed, or used, and then when it runs in the environment, it obviously is going to do its work, which is to take in more information than it is supposed to have access to. It actually does the same thing as Browserify too, so the developers actually feel behind the scenes that everything is working fine, but actually behind the scenes, what it's doing is also extracting out information. So this is one way on in which your dependencies that you use, you should be very careful, and you should be also trained on typo squatting to avoid people making intentionally just a letter here and there, and it's literally the same package but does a lot more than what you would like it to do. The second kind of attack, which was in this case something in the well-known logging library in Java called log4j. And this is a very different kind of problem, in a sense that, let's say log4j is currently at version 3 of its software. I'm just giving an example. Now, there was an older version of the software also available in the repository for version 2, let's say. And this was obviously used by a lot of companies, organizations, but later on, a bug, or basically a vulnerability, was found in version 2 of the software. So not many people are, or lots of people probably are using 2, but now it's moved on to 3, 4 and other versions. But in an older version, a particular vulnerability was found. As a result of that, right, all the organizations that have created the software using version 2 of the log4j library are now vulnerable, right? And if the attacker knows that, hey, let me check, any organization still using log4j 2 version, well, let's do have some fun, and basically they start attacking it. So this is not intentional, but also shows that if you have built your software using some older versions of libraries in which vulnerabilities have been discovered, then you will have to have a way by which you will have to upgrade the version that you use and build your software again, right? And it may not happen if you are just directly using log4j2 as an example out here. It can even happen as what you're seeing over here, very small difference in the diagram. But really speaking, this is like a package that you are using, which in turn depended on version 2 of the log4j software, as a result of which you will still be vulnerable, right? So it happens both. It's not just your direct dependency, but it could also be transitive dependency. That means dependencies that your dependencies are using to build out their code. So in both of these cases, yeah, the key thing to understand, and which is where we bring in the lessons, is that you have to know your dependencies fully. It's difficult task because so many dependencies, transitive dependencies, maybe you need to subscribe to some updates as you're seeing in point two, right? So it becomes very difficult for an organization to keep a track of all of these things, plus have their own private dependency repo, which is one of the suggested things to do. But at the same time, there are also services like Google Cloud's assured open source software. So we've got our own repository in which you check software for any vulnerability, then everything is good. We make these available to others and you can directly use it from there. That could be another way in case an organization is not able to manage it. Like I mentioned to you, it's important that as a developer, you're aware of typo squatting, or at least it's there at the back of your mind. Small changes in name, but it could cause a lot of damage. The other thing also to understand is that these packages, when you're trying to deploy them into or basically push them into your own repository or even run them at deployment time, there need to be services available that scan for any vulnerabilities or prevent running of any dependencies that are known to have issues. So, in the case of Google, the artifact registry as well as binary authorization, these are services I'll talk about a little bit later with the demo in terms of how they prevent these things from happening actively too. So that's our second point, which is manage your dependencies. The third thing, which is the end-to-end trust, right? And the example here, it's a very well-known one called SolarWinds for a couple of years or so back, but a fairly large attack. And the way it happened over here, if you focus on the left side, is that uh, one of the internal developers itself got hold of the key, as a result of which the attacker, for reasons best known to him or her, modified the code, put in some malicious things to get some more information like access to secrets, etc. They built the package and then they pushed it into the SolarWinds deployment process. As a result of which, the latest version that SolarWinds had at their site for download by customers was a compromised solution. So what you can see over here is that clearly the build process was compromised by the attacker internally itself. So there was probably no checks and balances done at that time as to, let me only deploy software or only make software available for download if it has been built by my process and not by anyone else from their machine. Those things are probably not there, as a result of which one of the attack vectors earlier that we saw, you could compromise the build process, inject your code, and make that binary available to others. So as a result of that, SolarWinds customers, they downloaded the software that had a problem. And then obviously once it ran in their environment, it did all of the things that it was not supposed to do, and the attacker got access to a lot of things that could potentially cause damage. So what this sort of highlights is the ability to manage the end-to-end process over here. So you have to know that every artifact that your process produces, it should be produced by you and it's not modified. So there needs to be a sequence of steps that have been used to build that artifact. It's typically known as provenance. That has to be attested by the build process so that you know that only if this metadata is available, I will go ahead and deploy it. Otherwise, I'm not going to even deploy it or use it in my, the rest of the release cycle. So Google Cloud, now coming to that, right? If you look at this end-to-end thing, it really addresses it at every point, right? From developing your software, building your software, deploying it, and obviously running it, right? So you've got like when you're developing it, cloud code. That's where you modify your code. We have a demo that will show a few of these things. It prevents building of the software also in case there are any vulnerabilities known in the dependencies that you're using. Similarly, if you push any artifacts in the artifact registry, we can even give you a vulnerability analysis. And finally, at runtime, as I mentioned, we will not deploy any package, any artifact which has not gone through these checks and balances. And that's done by a service called binary authorization. So right from development to build to deploy, there are checks and balances. And this is the entire end-to-end trust pipeline that we are talking, which results in a secure software supply chain. So, having said that, right, I've got a pre-recorded demo for you, and this is what it sort of highlights some of these factors. So, Before I go to the demo, just to settle down on the key messages that I wanted to give you, the three ones, let's reiterate them again. One is manage your secrets well, which is do not check your secrets into things like source code repositories or keep them as environment variables or even directly in your source code. Use dedicated secret stores for that. Manage your dependencies. This is about ensuring that you're completely aware about all the dependencies that you're using in your software, not just the dependencies directly you're dependent on, but even transitive dependencies. And obviously, end-to-end trust in the whole process is extremely important. So let's begin a demo over here, and that shows you some of these features.
Yeah, let's start with the developer environments. Cloud Workstations provides customized developer environments that allows developers to get up and running quickly with just the pieces that they need for a particular project. We can create custom profiles that can be set up within private networks. We can minimize data exfiltration risks, and we can customize the environment. So I can do things like select the CPU, RAM, and even GPU profiles that I need. I can also do things like select the IDE that's going to run. I can also select a completely customized container image, and that would allow me to fully have control over all of the tools running within that. We're going to be working in a Java environment, so I'm going to launch our Java dev profile here, which has all the tools I need, including the Eclipse Temurin JDK. I also have Maven installed, so we're going to be working within a Maven project today. I also have Artifact Registry's new remote repositories configured. Now, this allows for proximal caching of my dependencies for speeding things up. And I've also got that configured, of course, within my POM XML to read from that registry. So I can get started with my Maven work. Let's shift gears and talk about dependencies, and let's talk about securing those dependencies against vulnerabilities. Cloud Code has a new capability called Source Protect. Now, Source Protect will provide linting style, as you can see this kind of red underlining, linting style notification of vulnerabilities that are lurking within the dependencies that you define. In this case, I'm again looking at a POM XML file. I've got the Spring Boot framework here, and you can see all the various vulnerabilities that are lurking within those dependencies. Now, if I update one of the versions here, one of the main versions to something more current, you can quickly see that the count drops from 15 to 12 problems. And I can work through this POM XML and address all of these problems. Now, I'm not going to do that. I'm actually just going to go ahead and commit, and we're going to kick off a build within Cloud Build. Now, Cloud Build can be configured to run all those same tools that we just talked about. In this case, I've got my Maven builders there. I've also got Docker, and Docker is going to help me containerize my application and ultimately push to Artifact Registry the compiled image. Now, I've also configured a vulnerability scanning policy. On push, I'm going to be scanning for vulnerabilities. What this policy does is it will fail the build if that policy has not been met, basically if the thresholds are exceeded. In this case, you can see that it has. Now, we know that there was at least 12 problems still lurking there, and you can see that in this case, Cloud Build caught those problems, and we were able to stop the build without proceeding down toward a deployment. Now, we could take a look at the actual image that was produced, and this is stored and housed in Artifact Registry. Artifact Registry provided that vulnerability scanning, basically. On push, it automatically scans, and you can see that, in fact, aside from the 8 mediums, I have quite a few highs and criticals lurking here, both Maven and OS level vulnerabilities. So my vulnerability policy stops CI/CD from deploying this image, but what if I tried to deploy it directly with kubectl, so short-circuiting the CI/CD process? Now I'm going to do that, and we're going to try, but you'll see that it actually fails. And the reason my deployment fails is because I have a admission control policy set up that blocks any image that has not accumulated proper trust. Now, this is done by a system called binary authorization. Binary authorization can be configured to set out a policy where you can specify all the trust factors required. In this case, I only have two. I have that it be built by Cloud Build as one, and that we have a vulnerability scan as the second. So as a result, I'm going to have to just go through and fix all of the problems within this particular application. So I'm going to use Cloud Code here to help me do that. And you can see that Cloud Code will help me find not just the direct dependencies, but also ones like this, which is a transitive dependency. And that would be very challenging to find otherwise. So let's fast forward a bit. We've fixed all those problems, and now we can kick off another build by triggering it via push. And we'll do that now. And we'll see that once this thing finishes, it actually passed, and we were able to get through that vulnerability policy step and on toward a CD via cloud deploy. We can also take a look at a new capability called Security Insights within Cloud Build. This provides information such as the SALSA level that we attained, the build integrity of this particular item. So we can see that there's no vulnerabilities lurking here. We can also inspect all of the dependencies that are in this particular image. We can also look at the provenance of this image. Now, provenance think of it as the recipe. So this is all of the inputs, including all the build steps, including the builders that were used, like Maven in this case, and Docker. We can also see things like the fact that we went through that vulnerability policy step. My application has been deployed. It's running in GKE. Now let's take a look at the security posture a little more closely using the new security posture management capability within GKE. Now this provides an analysis of my running workloads on the various clusters I have. In this case, I have 3 clusters. I have 13 running workloads. And it looks at things like configuration concerns. Now, these are pod spec considerations. Also, of course, vulnerabilities. So this is a daily scan of OS vulnerabilities that comes with GKE. So I have a drill down interface where I can slice by various perspectives like concern or namespace workload. I can also do things like filter by severity. So in this case, I'm going to prioritize my time and focus on the most important things. In this case, I have a high CVSS score vulnerability with a fix at hand, so I can go ahead and remediate. I also know where to remediate. And this is one of the great things about security posture management in GKE. It ties together not just the problems, but it pulls them in to the context of where it is, where in your workloads these things reside. Let's take a look at our application, the Maven application we just deployed. And we can go and filter for that particular cluster. And I can see my demo app application. And I can see that there are actually 2 suggestions, some medium level suggestions. One is that we're running as root. The other problem here is that my pod security spec actually allows for privilege escalation. Armed with where it is and how to fix it, I can just update the YAML and make the changes to secure this particular workload.
All right. So this was actually the demo that we had. So this brings us to the end of the session that I had here. So the point that I wanted to make again is that the 3 key takeaways which were there, keep those in mind. The secrets, dependencies, and end-to-end supply chain security or trust. The important thing is right that to start now. Also look at this particular link that we've got that sort of discusses more about this topic. If it is of interest, you can see how various Google Cloud services also come together to make this happen. All right, then that's all I had from my side. Thank you and have a good rest of the day. Thank you.